Hello, everyone, and welcome. Today, we are going to be talking about the longest common substring, how we can solve that problem, specifically how we can do it in linear time. In order to do it in linear time, we need something called suffix trees. So the bulk of this specific presentation is going to be talking about what are suffix trees, how we make suffix trees, and then how all this can be done in linear time to eventually solve the longest common substring problem, right? Okay, so the longest common substring problem says that given two strings x and y are of total length n, over some constant size alphabet, uh, how do we compute the longest common substring between these two strings in linear time, right? Solution, we can easily do this in quadratic time using dynamic programming. Again, however, our goal now is linear time. The time can be improved in linear by the use of these suffix trees, right? So what are suffix trees, right? A suffix tree is nothing more than a way of organizing all the suffixes in a string, right? Um, uh, some properties of a suffix tree, right? There exists one leaf for each suffix of a string, right? So depending on what position you start at, so the string in Mississippi, right? Depending on what specific, so either first, second, third, fourth. Well, so Mississippi, so this string has 12 characters in it, right? So hence there are going to be 12 suffixes for the string. So hence, if you count all, the leaf nodes, you will have 12 leaf nodes, one for each suffix, right? Right. Okay. This dollar sign that you see within the suffix tree, that's nothing more than a termination character. That basically is just saying, hey, like this string is over, pretty much. That's all there is to it. The path label from the root to the leaf, number one, that's the full string, right? So that means we're starting the suffix at the first position of the string, while the suffix starting at the first position of the string is literally the whole string, right? And so that is what that is saying. And so more generally, we can say that the path label of any leaf number j, right, that's going to start at position j of that string. Sorry, I'm flipping through these so fast, or I don't know, my bearings are off, my bad. Anyway, so the leaf number j spells out the suffix starting at the jth position of the string, right? So if we wanted to find, say we started at this position, the fifth position of the string I, right? So according to this, the leaf numbered 5 that spells out the suffix starting at 5, right? So we look for I, so we come to I, and then we have SSI, and then we have VPI dollar sign, and that would be, the path for leaf number 5, right? Because starting at position I. For any node, the first character on a path out of that node, right? They're all going to be distinct, right? So for instance, let's take the root. So looking there are 4 edges coming out of the root. However, the first character of every single edge is distinct, and this pattern continues for all internal nodes within the suffix tree. The first character on the edge label of any of the outcoming edges from that node, any of the children, those children edges, whatever, the first character is always going to be distinct, right? So a path label, that's pretty important. The path label of a node is the label of the path from the root of the tree to that node, right? So if we wanted to find like the path label for this specific node right here, hopefully you can see my cursor, we just follow, the root down to that, and then, follow, the characters in order. So the path label for this specific node would be ISSI, right? And that's really all there is to it. The label, I know I threw out the term label. The label of a path from the root that ends in a node is a concatenation in order of the substrings labeling the edges of the path. You can basically just think about that, like what is the string on the edge? That's basically what the label is, right? Okay, cool. So those are some very useful properties that will really be important for when we talk about the construction of a suffix tree, right? So the construction of a suffix tree, right? How do we make a suffix tree, right? All right, remembering that our goal is to build a suffix tree in linear time, right? There's multiple algorithms that can do this. We have Conans, we have Weiners, we have McCreights. We can even construct a suffix tree through the use of a suffix array and a longest common prefix array, right? For this specific presentation, we are going to be detailing Eukonen's algorithm for suffix tree construction, right? So before we go into suffix tree construction, let's kind of go over a very naive approach, right? So we have our string of length n, right? So the first thing we do is we start at the first position of the suffix, right? And again, going back to what I said earlier, the first position of a string and building the suffix from that first position, that's nothing more than the entire string, right? So we put that in the tree. So now we have the entire string in the tree, right, for the first suffix. For all subsequent suffixes, right, we enter these kind of one at a time, starting at position I all the way through n into the tree, right? So let's let ni, that's going to denote the intermediate tree that is encoding all the suffixes from 1 to I, right? We construct the next tree, so ni plus 1, construct as follows. So we start at the root ni, right? So now we want to find the longest path from the root, which matches the prefix of si plus 1 to n, right? So there's two things that's going to happen when we're finding this longest path. Either there's an exact match, right? So we end up ending at a node, right? Or we're going to end in the middle of an edge, right? So if we end in the middle of an edge, we are going to break that edge into two edges, right? By inserting a new internal node v, right? And that internal node gets inserted after the last character that matched exactly. Put a new node there, make a new edge for the characters that didn't match, right? That's the naive approach, fairly basic, pretty easy to follow. And this approach is taking quadratic time, right? So not great, not what we want, but this gives us somewhere to start, right? And Eukonen's algorithm is loosely based off of this naive approach, right? You will definitely see some similarities as we go through it, right? So before we start talking about Eukonen's algorithm, let's first talk about what an implicit suffix tree is, right? So to construct an implicit suffix tree from a suffix tree, you basically do three things, right? The first thing that you do is you strip the termination character from all the edges, right? So that $, take it away from, just take it out the tree completely. Like there should no longer be a $, in the tree when you have the implicit suffix tree, right? So when we strip the $, we're going to have some edges with no labels, right? Okay, so the next thing we do there is we take away all the edges that have no labels, right? And so what that's going to do is that's going to cause some nodes to have fewer children, right? And so the last step for building an implicit suffix tree is that if a node does not have at least 2 children, then we throw away that node, right? And then we have our implicit suffix tree. The implicit suffix tree for a prefix of s, it's also defined in the exact same way. You follow the exact same steps and you get an implicit suffix tree for a prefix. And we're going to denote the implicit suffix tree by this ti, right, for a string 1 through I, right? So here's just an example of how we get from a suffix tree to an implicit suffix tree. So we strip the $, away, clearly we strip the $, away. That leaves us with some empty edges, take those away, right? And then that leaves us with some nodes whose degree is less than 2, right? And so then we take those nodes away. And then we have our implicit suffix tree, right? Pretty basic, but that's very important for how Eukonen's algorithms works. So at a high level, we can construct a suffix tree ti for each prefix s1 through I of s, right? And we start at t1. T1 is nothing more than the first character, right? The true suffix tree is going to be constructed from the last implicit suffix tree built, and we're going to claim that we can do that in linear time, and that is what we are going to show in the remainder of this presentation, right? The algorithm is divided into n phases, right? So a phase for each character, and in phase I plus 1, we're constructing implicit suffix tree I plus 1 from implicit suffix tree I. So from the previous implicit suffix tree, right? That's how we're building the new implicit suffix tree, right? This third main bullet, I should say, is kind of where the magic takes place. The extensions these things called extensions are where we are actually extending the suffix tree. It's where we're adding new characters, or we're adding new nodes, leaves, edges, all that good stuff, right? So in phase I+1, we're dividing it further into I+1 extensions, right? So we have one extension for each of the I+1 suffixes, right? So in extension J of phase I+1, we are finding the end of the path from the loop, from the root labeled with the substring J through I, right? So we're finding J through I. We want that path. And then we extend that by adding the I+1th character to that path unless the I+1th character is already present, right? So, so J is a loop. So in phase I+1, right, we're putting 1 through I+1 followed by 2 through I+1 through all the way up to I+1 to I+1, which is just the last I+1 character into that tree, right? This is a high level of how the algorithm is working, but we are going to go in much greater detail. So bear with me. This is taken from Dan's Gusfield's textbook about suffix trees and stringology. This is basically everything I just said, just in a little bit more formal pseudocode way. So feel free to pause the video and take a look at this if you need to. So when we are extending the suffix tree, we extend it according to these 3 rules, right? Okay, so all right, let's get into it, right? So let's let the substring S, J through I, we're gonna call that beta. That's gonna be a suffix of the substring S, 1 through I, right? So in extension J, when we find the end of beta, so we find the end of beta in the current tree, right? And then we're extending beta to include the I+1 character, right? And then that's gonna be done according to one of these 3 rules, right? So okay, these rules are pretty formal, but I'm going to try to break them down to you in pretty simple terms, right? So okay, rule 1 says that in the current tree, path beta ends at a leaf. So if you followed beta in the current tree, you end at a leaf. So that is the path from the root labeled beta extends to the end of some leaf edge, right? To update the tree, character I+1 is added to the end of the label of that edge. Okay, what does that mean? Basically, rule 1 just says add the I+1 character to the end of each leaf edge, right? And here's a basic example. So say we wanted to add B. So following the green, don't worry about the purple for now. Following the green, we're doing nothing more than adding this character to the end of every single leaf edge. That's basically all that rule 1 says, right? Okay, rule 2. No path from the end of beta starts with I+1, right? So no path. So you find the end of beta, but there's no path that starts with I+1, but at least one labeled path continues from the end of beta. So while it doesn't start, it keeps building upon beta, right? So okay, so rule 2 says that a new leaf edge starting from the end of beta must be created with label I+1, the I+1 character, right? A new node will also have to be created if beta ends inside an edge, right? The leaf at the end of the new edge is given the number J, right? So, okay, so what does rule 2 say? Rule 2 says sometimes we add a leaf, sometimes this will create a new node, right? So if you find beta, but beta doesn't end, right? So the path still goes on. And if you say you're at the end of a node, well, you either add the I+1 character as a new leaf edge, or beta is ending in the middle of an edge, to which case you create a new internal node whose leaf edge is now the I+1 character, right? So for example, rule 2 here says that if beta was, equal to X, for instance, okay, so we found X, oh, but wait, that's in the middle of an edge. So we have to create a new internal node and label that edge label B, right? And then that's J, right? We label it J because that was the 5th extension, right? But that's all rule 2 says. That there's nothing more to it than that. Okay, so rule 3 says that some path from the end of string beta starts with the character I+1, right? So that means that the string beta with the I+1 character at the end of it, it's already in the current tree, right? So in that case, we don't have to do anything, right? So using these rules that were just described, so once the end of the suffix has been found, right? We only need constant time to execute these rules, right? So this is great because now we have a method to extend a suffix in constant time, right? The only problem with this currently is that we have to traverse the tree from root to leaf in order to extend it, right? So in order to do the jth extension, right, we have to find the end of the path, right? So again, yeah. So basically, what this says, we start at the root. We have to traverse down to find each beta, right? And this is bad, right? Because this takes cubic time, right? So in order to bring this down, we introduce what we call something called a suffix link, right? Okay, what is a suffix link? All right, so it's pretty formal, but bear with me. So a suffix link is given as follows. So we let X alpha denote an arbitrary string, where X denotes a single character and alpha is a possibly empty substring. From an internal node V with path label X alpha, if there exists another node S of V with path label alpha, then a pointer from V to S of V is called a suffix link, right? And this is just a property. Every internal node of an implicit suffix tree will have a suffix link from itself. So here we have an example of a suffix links, right? So here we have X and our alpha, right? So again, what are the suffix link said? From an internal node V with path label X, there exists another node whose path label is alpha, right? And we can see that the path label of this node is exactly alpha, right? So then we can draw a suffix link from this internal node V to this internal node, which we're going to call S of V, and that's how a suffix link is determined, right? It might not be immediately apparent in terms of as to why we need suffix link, but suffix links are very important, and they allow us to make use of some exploits within the suffix tree that will eventually get us down to a linear runtime algorithm for suffix tree construction, right? So here we have some properties of suffix links, right? These are all stated very formally, but so just bear with me again. So if a new internal node V with a path label X alpha is added to the current tree in extension J of some phase, then either the path labeled alpha, it already ends at an internal node of the current tree, or or an internal node at the end of a string will be created. So, or we're going to have to make a new internal node in the J+1 extension of the same phase, right? This new internal node is being created by the extension rules. It's coming from extension rule 2 primarily. So any newly created node is going to have a suffix link from it by the end of the next extension, right? It's just another property of suffix links. And then any implicit suffix tree, if internal node V has a path label X alpha, then there is a node S of V in the implicit suffix tree, the current implicit suffix tree with path label alpha. Just some properties that make suffix links a lot easier to work with, right? So why even use suffix links, right? So recall that during the jth extension, we are looking to match the substring Sj through I along a path from the root in the current tree. And again, the only way we have a mechanism to do this is to continuously start at the root and walk down until we find that match, right? Again, that's no good, right? But suffix links allow us to shortcut this walk and each extension, right? So suffix links, we no longer have to start at the root, right? So to find the J through I substring, so we start at the end of the path, the previous J, right? So we walk up an edge to the node V, and then we follow that suffix link to S of V, and then from there, we continue to walk down, right? So, okay, so here's an example, right? So before we had to start at the root, we had to walk all the way down, right? again, that's no good. But if we have to do that every single time, we get terrible runtime. We get cubic runtime. According to suffix links, though, what we're allowed to do is we're allowed to start at this v, right, and then we jump to the suffix link, right, that shares a similarity, and from there we can continue our walk down, right. That's where a suffix link is. So a suffix link is allowing us a better way to traverse the tree rather than starting at the root every single time, right? This is what a suffix link is, right? And with using suffix link, we're able to make some exploits. So a suffix link by itself, that's not going to let us improve the time bounds. It doesn't improve the time bounds, but there's a specific trick that we can do to bring the runtime down to quadratic, right? Order of n squared. We call this the skip count trick, right? So when traveling down from S of V, right? So from the suffix link. So when traveling down the node S of V to a leaf, right? So if the number of characters on the edge is less than the number of characters that we need to travel, just skip to the next node, right? Just don't even worry about it. Skip to the next node. On the other hand, if the number of characters is more than the number of characters that we need to travel, we'll just skip to the last character on that edge, right? So clearly this makes traversing the tree significantly easier because we can just keep skipping things, right? So this allows us to move from one node to the next on the path Y in constant time, right? I have an example after this, right? So the total time to now traverse this path, right? That's going to be proportional to the number of nodes, right? Because the number of nodes basically is determining how much we skip, kind of, right? So here's a great example, right? So we have our node V, and we have this substring Y, right? And we want to traverse, right? So we use our suffix link to skip to this node A, right? Because they share the same path label. And we want to traverse all the way down the entire length of this substring, right? So, okay, well, that's less, so skip. Okay, that's less than we need to travel as well, skip. This is also less than we need to travel as well, skip to this node. Okay, now we have 3 characters, which is which is JK, and so we have 2 here. We only need to go 2 more places, but this is 3, right? So again, following the skip count trick, just skip to the last character, boom, and okay, now we're done, right? So that's how the skip count trick works. That's how we are traversing the tree. So with this, we are allowed each phase is taking linear time, right? So we have n phases, thus we have big O of n squared time. Now you might be thinking like, okay, why? So like big deal. Okay, now we're at n squared. Now we're back at the dynamic programming or the naive approach. Things will start to make more sense. Well, we still have a few more things to go over. But however, so we currently have 2 big components right now to our linear time recipe, right? So the first component, we can extend a suffix tree in constant time, right? Based on the extension rules that we previously discussed. The second component now, right? We have this skip count trick. We have these suffix links that allow us to more efficiently walk down the suffix tree in each phase in linear time, right? So we have 2 specific components to the recipe. We have constant time to extend the suffix tree, right? And then we can walk down or do each phase in constant time, right? So currently we have the problem where the suffix tree occupies n squared space, right? So this doesn't really bode well for us if we're looking for a linear time algorithm if our tree is occupying n squared space. But we can fix that with this thing called edge label compression, right? So currently it's occupying n squared space just because there's potential for the edge labels to contain more than linear O of n, big O of n characters. So say it's like if we have a string, right, that represents the entire alphabet, so A, B, C, D, E, F, G, right, all the way to X, Y, Z, right? So each suffix of that string, that is going to begin with a distinct character. And so if you remember with one of the properties of suffix trees, right, every single edge from a node starts with a distinct character, right? Okay, so what does that mean? That means the root itself is going to have 26 edges coming out of it, right? Each being labeled with a complete suffix, right? Okay, so this requires 26 times 27 over 2 characters, right? That's huge, right? So that's where the n squared space is coming down, right? Okay, but again, we have something called edge label compression, right? So instead of writing the substring on each edge, what we instead do is we're gonna write the pair of indices that correspond to beginning and end positions of that suffix, not suffix, of that substring, right? So now every single edge can be written in a constant number of symbols, right? The extension rules, those follow in the same exact manner, right? And then with this, we only need constants, or not constant, we only need linear space, which is going to make a linear time algorithm much more plausible, right? So here we have an example of edge compression, right? So on the left, we have the explicit representation, I guess I will say. And then on the right, we have the edge compression, right? So for instance, this first path label, ABC, right? So we just represent that as 1, 3. This example isn't like immediately clear in terms of why, because right, in some cases we're representing a 2 labeled path with 3 new characters, right? But going back to strings such as Mississippi, right? Some really long strings that have long path labels of many characters, right? Excuse me. This edge label compression makes it a lot easier, right? Because now instead of saying you need like 12 characters to represent a path label or a label of an edge, oh, now you only need 3, right? Which is great. So yeah, that is edge label compression, right? And so when we're following the extension rules, there are 2 observations and exploits that can be made to achieve a desired runtime, right? The first observation is that rule 3 is a showstopper. That is literally the name of it. Pretty funny name if you ask me. Rule 3 is a showstopper, right? So in any phase, if extension rule 3 applies in extension J, well, it will also apply in all further extensions, J plus 1 through I plus 1 until the end of the phase, right? So if we remember what rule 3 says, the path labeled J through I in the current tree must continue with the character S plus 1I, right? So rule 3 says it's already in the tree, so you don't have to do anything. And so the path labeled J plus 1 through I, that also has to be in the tree, right? Just based on rule 3. So therefore, rule 3 is going to be applying to extensions J plus 1, J plus 2, all the way to the I plus 1 extension, right? And again, observation 3 is saying that we really don't need to do anything, right? Okay, maybe I was getting a little bit ahead of myself. So remembering that we do nothing in rule 3, a new suffix link needs to be added to the tree only after an extension in which rule 2 applies, right? Because rule 2 is applying a new leaf edge and a potentially is also creating a new node, right? And that's only in rule 2, right? So trick 2 says that in any phase, that the first time that the rule 3 applies, so the first time that you do nothing, you end the phase over, right? So if that happens in some arbitrary extension J, right, there is no need to find you don't need to explicitly find the end of any substring K through I where K is greater than J, right? Because those extensions, those are already present in the tree implicitly, right? This is where the name, the implicit suffix tree comes from, right? Each suffix need not be represented in the implicit suffix tree explicitly, right? So rule 3 is basically saying that, hey, once you're done, all further substrings that this applies to, like those are already in the tree implicitly. Don't even worry about it. That's the first trick, right? Okay. Second observation that we can make. Okay, so once there is a leaf, so once a leaf, so once something is considered a leaf, you're always going to be considered a leaf, right? So if at some point a leaf is created in label J, right, that leaf, that is going to be a leaf in all successive extensions or subsequent continual extensions, whatever, all extensions past that. That leaf is going to stay a leaf during the entire algorithm, and that's I don't necessarily know if I should say that's by design, but the algorithm itself has no mechanism to extend a leaf edge beyond its current leaf, right? So it has no way to take a leaf edge and all of a sudden insert a node at the end of that leaf edge, right? So again, once a leaf is labeled, that leaf is always going to be a leaf. Now the path label of the leaf might become extended, like in rule 1, where we just append just the last character, the I+1 character. So again, the path label might get extended on the leaf path label might get extended, or the leaf edge label, but it's always going to be staying a leaf, right? So again, so kind of going through somewhat of an example. So leaf 1 is created in phase 1, right? So and then in any subsequent phase, there's a bunch of extensions that happen, right? Where either rule 1 or rule 2 applies, right? So we let j sub I denote the last extension in this sequence, right? So the last extension that happened where rule 1 or rule 2 was applied. So remembering that rule 2 is always going to create a leaf, and in some cases it's going to create the internal node. We can say that j sub I plus 1, that's going to be greater than or equal to j sub I, right? In the case where j sub I and j sub I equal, this is implying that rule 3 is applied, right? Because we added no new leaves in this current phase, right? So we see that in the current phase, rule 1 will apply an extension 1 to ji, and extension ji plus 1 onwards. Rule 2 may apply, followed by rule 3, and then rule 3 is going to end the phase, right? So what is the exploit that we can make by this observation? So remembering that we're doing edge label compression now, right? So we can represent these edge labels as two indices P and Q, right? Which is specifying that substring SP through Q, right? So index Q is equal to I in phase I, and then gets incremented to I plus 1 in phase I plus 1, right? Reflecting the addition of that I plus 1 character, right, to the end of the suffix or to each suffix, right? So trick 3 says that in any phase I, the leaf edges are going to look like PI, QI, RI, right? Because those leaf edges, that character on that leaf edge, that's always the final character, right? Because that's what a leaf is. It's the end of a suffix, right? So that's always the final character, right? So in phase I plus 1, right, these edges are going to be updated to PI plus 1, QI plus 1, RI plus 1, so on and so on, right? If we were to increment these, one by one, we would have to traverse the entire tree to all the leaf edges, right? And we have to increment them accordingly. Well, that kind of sucks, right? Because that means we'd basically have to start at either the root or use suffix links to update all these leaf edges accordingly, right? And that does not bode well for runtime at all. So to do this in constant time, we know we can just keep a global index E, right? Where E is equal to like our current phase number. And then we instead, we label our leaf edges as PE, QE, RE, right? So, whenever we enter a new phase I plus 1, phase I plus 2, phase whatever, right? Well, so instead of literally traversing the tree and looking for every single leaf edge, right? Well, why not just increment E by 1, and which basically automatically takes place of all the leaves, right? So now we have a mechanism to update all the leaf edges in constant time, right? So, we are even closer now to getting a constant time run algorithm for a suffix tree, right? So now we can put it all together, right? So we have our explicit extensions in phase I plus 1. So those are only required from extension ji plus 1 until the first execution where rule 3 applies, right? So all the other extensions, which we previously gone over, like all that's done implicitly, right? The only time you need to explicitly extend something is after that j sub I plus 1, right? And until rule 3 applies, right? So using these suffix links, right, and which allow us to traverse the tree in a much more efficient manner, and these implementation tricks, so we can build the suffix trees T1 through Tn in linear time, right? All the implicit extensions, right, those are done in linear time, right? The explicit extensions, those can be done in constant time, right, proportional to the number of nodes skipped, right? Again, and that's coming from the skip count trick, right? So that itself is also bounded by big O of n, right? So with that, so the nth implicit suffix tree, we can, right? So all those trees are computed in constant time, right? And then we can convert the last implicit suffix tree to a true suffix tree in linear time as well, right? And that's not hard to do at all. Really, all you have to do is you add the terminal character, you add it to the end of the string, and then you let the algorithm, you let it continue with this character, right? So no suffix is now, so because we add the terminal character, right? So no suffix is now a prefix of any other suffix, right? So now we have an explicit representation of each suffix in the suffix tree, right? And again, we're replacing the index, leaf edges with the number n, right? But that's done in linear time as well, right? So now we have our suffix tree, right? We have our true suffix tree, which we just shown can be computed, not or not computed, but built in linear time, right? So with that, we can now move on into how do we solve the longest common substring problem, right? So the longest common substring, right? We have our two strings, x and y, right? So what we do is we combine these two strings, right? Or we concatenate them together. So s is now x plus y, or x concatenated with y, right? We build a suffix tree for s, right? That's done in linear time. Very important. Remember, we just proved that, or we basically just showed that. We showed that we can build the suffix tree in linear time, right? So every leaf in this suffix tree is indexed by its position in S, right? And that's done through edge label compression, right? So because we concatenated these two strings, right? So we know the positions, right? We know where n, or where the position where X ends and Y starts, right? So that means we know which leaves are coming from X and Y respectively, right? So in order to find the longest common substring, right? The longest common substring is nothing more than the longest path to a node who is an ancestor of a suffix coming from both X and Y, right? Okay, we can label that. So the goal is to basically find that node, right? So it's okay, so how do we do that, right? So we label each node to basically say which string its descendants came from. So there's three ways that a node can be labeled. It can be labeled as X, it can be labeled as Y, or it can be labeled as X comma Y, right? Signifying that this node contains children that come from string X and string Y respectively, right? All we have to do to find the longest common substring, we do a depth first traversal, find the deepest node, label XY, which gives us the longest string depth, which in essence is the longest common substring, right? So then now we solve the longest common substring problem, right? So that's basically it. So these are just some references that that I used to help build this presentation. That first YouTube video, that's a presentation by Dan Gusfield himself, just basically telling you what is a suffix tree, what are they used for. There's tons of applications suffix tree. Highly recommend. The second reference, that's Dan Gusfield's book. So a lot of the material I took for this presentation came from that book. That book goes into much more formal detail than I did. It contains proofs for some of the statements that I said and things like that. Geeks for Geeks also has a phenomenal description of how Uconen's algorithms work. Geeks for Geeks also contains a few little implementation details that are very important to Uconen's algorithm as well, in terms of, when you're actually writing the code and everything like that. So with that, I hope you learned something today. I hope you learned, at least took away what a suffix tree is and the general idea of how a suffix tree is constructed. And then maybe you see a few ways that a suffix tree can be used in, in whatever algorithms you decide to work on. So I appreciate you all. Thank you. Have a good one.